I'll start the recording here. This, when I said don't use limits and use infinity, a little different problem than this one.
Mm-hmm.
This one has a problem because you can't go from -8 to 1 on a continuous function. There's an asymptote at 0.
Yeah.
So you have to approach the asymptote, and then you have to add on to it on the other side of the asymptote. So this is really kind of a whole different method of using the limits. In other words, the reason you lost a point on this is merely because you didn't put the limit as a goes to 0 from the left side.
Okay.
And that's a right there.
With plugging a in, is there anything special to do? Because it just seems like sometimes it works and sometimes it doesn't.
No, this one is, in other words, this is a, and it's the limit as a approaches 0 from the right. The second part of it.
Okay.
And that way we kind of jump over the vertical asymptote that's x equals 0. Well, if you do both of these, this becomes 3a to the third. And remember, we're taking it as a goes to 0 from the left, so this term goes to 0.
Okay.
Okay, and you get plus 3 times the cube root of 8. Well, the cube root of -8 is -2, and -3 times -2 is 6, plus 3. In other words, this quantity over here, the same thing happens. If we take the limit of that as a goes to 0 from the right side, this term goes to 0. And so you're left with 3 times the cube root of 1, which is 3. So this whole thing should be 6 plus 3, or 9. Okay?
All right. I think I get that one.
Okay. That's a little different than taking, that's funny, they said minus, oh, it was -8. Okay. That's a little different. That's not actually an improper integral.
No.
An improper integral is defined as one where infinity is one of the limits of integration. And this does not have infinity as one of the limits of integration. But it goes across, in other words, it spans a non-continuous function. And maybe that is what an improper integral is also. My book says an improper integral is one where you have to have infinity or negative infinity at least one of the limits of integration. And that's kind of a different scenario where you substitute a letter for the infinity and you let the letter go to infinity. It's kind of a different problem. On those kind of problems, they work just fine if you just put infinity in. It's
Okay.
a little different. This is a harder problem because it goes across a non-continuous function. Okay, number 2, it looks like you got completely right. You compared it to 1 over x to the 5th, which we know is a convergent series because it's a p series with p greater than 1. And if we can prove that our integral is less than 1 over x to the 5th, then we will have proved that it converges because it's always less than a convergent series. And looks like you did. Is all this writing hers or yours?
That's mine.
Yeah, I didn't see any negative off of that, so I figured you'd gotten that one right.
Yeah. Yeah.
All right, number 3. Number 3 made me appreciate infinite series because I had forgotten how to handle number 3. Well, this is how you handle it. And I mentioned this a little bit last week, okay? So that's equal to the sum of 1 over e to the 6n, correct?
Mm-hmm.
And, or, actually I don't need to write it like that, but that is what it is. The important change to make is that it's e to the minus 6 to the n power. That's the equivalency that's important. The reason being is that now we have a geometric series. Anytime we have a number, and that's all e to the minus 6th is, it's a number, e is a number, to the n power, that is a geometric series. So this converges if what? What does it take for that to be convergent?
Not sure.
Well, it takes what's in parentheses there. The absolute value of that has to be less than 1. In other words, if we have a number greater than 1 there, it's just going to blow up, right? I mean, if I had 2, the first term would be 4, the next term would be 8, and so forth and so on. So it's going to blow up to infinity very quickly. So the only way these things are convergent is if you're taking a number less than 1. Because when you start taking numbers less than 1 to an exponent, they get smaller. In other words, if I have 1/2 to the n, well, the first term there is 1/2, the next term is 1/4, the next term is 1/8, and so forth. And this is a convergent series because it is a geometric series where r, the absolute value of r, is less than 1. As long as the absolute value of r is less than 1, you have a convergent series. Okay? So, by rewriting it like this, that's r, e to the minus 6th. So, if e to the minus 6th is less than 1, then that's a convergent series. Well, e to the minus 6 is 1 over e to the 6th, which is 1 over 2.71 to the 6th power. Clearly, that's less than 1.
And then the sum, given that it converges, is that 0?
No.
Or no, it couldn't be.
Remember that the sum is equal to a over 1 minus r. And in this case, a is 1. There's no coefficient in front of e. So in this case, we can say it's 1 over 1 minus r. Okay, well, what is that? That's 1 over 1 minus, remember r is e to the minus 6th, which is the same as 1 over e to the 6th.
And that's the sum?
That is the sum. However, there's a problem with that. And it's worth going through the algebra because that's not a simplified rational quotient. We have 2 terms in the denominator.
Mm-hmm.
So, first of all, combine the 2 terms in the denominator. We have a common denominator of e to the 6th. This becomes e to the 6th minus 1. You with me?
Yeah.
Flip it, multiply, you have e to the 6th over e to the 6th minus 1. That is a simplified rational quotient. And that's your sum.
Okay.
Okay. This would have probably also been accepted by your teacher.
Yeah, she usually takes unsimplified.
Yeah, and I didn't even realize, in fact, you've written that there. Problem is that you wrote it was divergent. And if something is divergent, then it can't have a sum. So it doesn't make any sense to say that the sum is this if it's divergent, because if it's divergent, the sum is infinity. Understand?
Yeah.
Okay. Number 4. She didn't take points off, but she really should have. It is divergent because R is what?
R is what? 4, 3 to the n?
It's just 3.
Just 3,
Yeah, in other words, only the 3 is taken to the n power. The 4 is not. I can actually write that sum with the 4 outside. It's just like an integral. You can take a constant to the outside. Okay? Or you can leave it inside, and that's A. Remember, the standard is A times some R to the nth power. So the R in this case is 3. That makes it divergent instantly. In other words, you should erase this. If it was convergent, it would be 1 over 1 minus 3, not 4 times 3. Actually, it would be 4 over. Since A is 4, the 4 would go in the numerator, and in the denominator, you'd have 1 minus R, well, R was 3. But this makes no sense whatsoever if it's a divergent series. She didn't take points off because you got the divergent right. If you'd had convergent up here, you'd have gotten full credit for it. All right, let's go next page. You lost 2 points here because you didn't have what it converged to, which you actually had the sum correct. In other words, the sum was minus 1 to the nth. That makes it alternating. But then A is 9, and R is minus 1/3. Okay? So remember what our sum is. Our sum is A over 1 minus R. Well, what would that give us? So
9 over
4/3, or 27 over 4. There's your sum. Now, it's worth saying, because it's not always obvious to somebody just starting infinite series, but the key thing to determine with infinite series is whether it converges or diverges. And there's only certain series that we can actually figure out what it converges to. And the geometric series is one of those. The geometric series is a beautiful series because not only can we tell if it converges, but we know what it converges to based on that. So usually, if it's not a geometric series, they won't ask you what it converges to because we don't know. In other words, most of the time with most series, you can either tell they converge or diverge, but it's not easy to figure out what they converge to. So the geometric series is special in that sense. All right, let's see. Number 6. You correctly decided that the absolute value of what's inside the parentheses has to be less than 1, which translates to that inequality, and you solved it correctly. So as long as x is greater than minus 4 or less than 16, then what's inside will be less than 1. And then we have a geometric series that's going to converge. If we're outside of this range, then what's inside the parentheses is going to be greater than 1, and it will diverge. Number 7. find the function represented by that series. Let's see, find the function for those x for which the series converges. Okay, hold on, I did this one. I just can't remember how I did it. Hold on. Yeah, this is an interesting problem. What does this series converge to? That's why this is a really interesting problem. In other words, if you look at this table, you'll notice that 1 over 1 plus x converges to 1 minus x plus x squared minus x cubed. Okay? Ad infinitum. It's worth memorizing these functions as to what their series expansion is. Well, notice that what we're looking at, hold on a second. That expansion is an alternating series, right?
Uh-huh.
Well, clearly we have an alternating series because the minus 1 to the n makes it alternating. So, let me see if I can explain this. If I said to you that this function leaves you with the alternating series 1 minus x plus x squared minus x cubed dot dot dot. Now if I said, well, what is 1 over 1 plus 2x equal to? What would you do?
Double everything.
Well, you'd plug in 2x wherever you saw x. So it actually would become 1 minus 2x plus 4x squared minus 8x cubed and so forth. And this is one of the most powerful capabilities of being able to take a function and write it as an infinite series, is that you can take alterations of that function and write those as a different, without going through Taylor's polynomial and resolving this completely, is all you have to do is take 2x and insert it for x, and you have the new infinite series. Or I could do 1 over x squared. I'm going to substitute x squared for x wherever I see it. Well, in this series, so if I say that 1 over 1 plus x is equal to this, that's true, right? As long as the absolute value of x is less than 1, then that's an alternating geometric series. And it is this series that we see on this page right here. Notice that this series, expands to this.
Uh-huh.
Well, what are we looking at? We're looking at, instead of x minus 6 over 10. That's the only difference between this series and this series. So if I have something that says minus 1 to the nth times x minus 6 over 10 to the nth, that's a geometric series, an alternating geometric series. So we should be able to write that as 1 plus x minus 6 over 10, which is r. The only reason you lost a point on this is because you had a minus instead of a plus. In other words, you treated this just like a normal geometric series, and you came up with the sum by using 1 over 1 minus r. But if it's an alternating series, that's not the case. An alternating geometric series does not give you 1 over 1 minus whatever's inside the parentheses. It gives you 1 over 1 plus. In other words, change that minus to a plus, and now what you're doing is essentially writing that function, only instead of x, we have x minus 6 over 10. All right, let's go on. We got this one correct. This one's pretty easy. You just did it straight out. Took the first 4 derivatives, evaluated them, and figured out what their coefficients were.
Let's see. I eliminated a couple of them.
In other words, this looks like the first derivative.
Yeah.
This is the second derivative. And then you're going to evaluate those at 0 to figure out what the coefficients are. You're going to plug it into the Maclaurin series and see what you come up with. Now, you've got to be a little careful here when you do that, because remember there's a denominator in the Maclaurin series. It's not just about the numerator. And there was another problem on here where you missed it because of...
Yeah, I missed a couple of those.
The one where you answered minus 5 when the answer was minus 30. And that's because 6 was the denominator. So in order to get a minus 5, we had to have a minus 30 over 6 in the numerator and denominator to end up with the minus 5 that we had. So be a little careful, and this is going to give you the same problem. In other words, each of these terms is combination of their numerator, which is the derivative evaluated at 0, divided by 6 factorial or 3 factorial right there. So you have to combine those two numbers in order to figure out what the final coefficient is. This is pretty straightforward. Looks like you did it very straightforward and you got it right. That's a 2 factorial there.
Yeah.
Is the same as 2, but I noticed you missed another problem by leaving out a factorial sign. This one right here. E to the x is x squared over 2 factorial. Ah, you did that intentionally.
No, she wrote that in, actually.
Okay, but I mean, when you put 2 down there, you knew that factorial was 2, so you didn't bother to write the factorial. But the factorials, I wouldn't say it's important. It helps to memorize it. Okay?
Okay.
Do you have all these memorized, or did you write these from the book?
No, I had to memorize those.
Okay, good. Notice the difference between sine and arctan.
It's just the factorial, yeah.
That's the only difference. The arctan is missing the factorial sign on the bottom, whereas the sine has the factorial sign on the denominator. So those two really make it easier to remember one if you can remember the other. Okay, let's see. Where did we want to go next? This was second page. I think we want to go. Yeah, here. Yeah, this is the example that I was talking about. Minus 5 is the final coefficient of the x cubed term. But we know the x cubed term started with a 3 factorial in the bottom, correct?
Yeah.
Just like the x to the 4th term starts with a 4 factorial in the bottom and a 5 factorial for the next one. So if I assume that that started with a 3 factorial, which is the number 6, then minus 5 has to be that f triple prime of 0 divided by 3 factorial. And so minus 30 is actually the f triple prime of 0. And that ended up giving us a coefficient of minus 5. Before we, I want to do number B, but I don't want to forget to do number 4. Number 4 is a very interesting problem. When I first looked at it, I said, oh geez, this is going to be a ton of math because we've got the product of two things. So I'm going to have to find all these derivatives using the product rule. And it's going to get very complicated and blow up pretty fast. First derivative is easy enough. The second derivative becomes harder, the third derivative harder, and so forth and so on. And I kind of felt that there had to be an easier way to do it. And after thinking about it for about a half hour on my couch, I realized there is. What is the series for that?
X minus x cubed over, let's see, 3 factorial plus x to the 5th over 5 factorial, and so on.
Stop there. What's the sign of 2x?
2x. Well, just put a 2 in front of all the x's.
And the parentheses are very important. Not a 2x in front of all the x's, it's a 2x in place of all of the x's. So now, what is this whole thing multiplied by x? That x right there. 2x squared minus, well, this was 8x cubed times x must be 8x to the 4th over 3 factorial plus, this is 32x to the 5th times x, so that becomes 32x to the 6th over 5 factorial, and that should be enough to tell us what our answer is. Sure enough, E. In other words, this illustrates a hugely valuable property of representing functions by infinite series. We don't have to do this the hard way. The hard way took me 20 minutes, and I did it. And even after doing it the hard way, there were so many calculations that I figured that I was at least 50-50 to have made a mistake. And sure enough, I came up with, I was off by a factor of 2 in that coefficient. And I didn't know what to do. I just assumed I'd made a mistake. But then I realized afterwards, thinking about it, that I could use the infinite series as a substitute for sine of 2x. And then, since the infinite series is a function of x, I can multiply each term by x to come up with the infinite or the Taylor series for this function. So it kind of shows you the robust power of using series. You don't have to do them always the hard way. All right, let's go back to 3. The only reason you missed 3 is because you made a math error. And it's not that difficult to make a math error here. It's actually pretty easy. When I did it the first time, I made the same math error that you made. What's the first derivative?
One over 3 minus x.
Times the derivative of the inside, which is?
Negative x, so negative.
Okay. And this is minus 3 minus x to the negative 1. So what's the second derivative?
Let's see.
Start with the x bar.
Yeah.
Multiply it by the coefficient. So that becomes plus
3 minus x to the negative 2.
Times the inside.
Make it a negative.
And f triple prime. Same thing happens. Minus 2 times the minus starts it out positive. We end up with 3 minus x to the minus 3 times the derivative of the inside. Every derivative has a negative sign in front of it. That's why B is the answer. B is the only answer that every term is separated by a negative sign. In other words, your first derivative evaluated at 0 is going to give you a negative number. Second derivative evaluated at 0 is going to give you a negative number, and the third derivative is going to give you a negative number. So that's how you end up getting B. I think probably the only mistake you made was when you took this first derivative, you didn't multiply it by the derivative of the inside. In other words, you have to apply the chain rule here. It's 1 over 3 minus x times the derivative of 3 minus x, which is minus 1. This one, I was surprised you got wrong, because I know you know how to do this one. You must have just made a simple error. In other words, they don't even make you, well, they don't give you the function, so you can't really figure out the Taylor polynomial, but we know a Taylor polynomial is made up of this. And so forth, right? Well, they give you, well, excuse me, instead of x, it's x minus 3, since it's a Taylor polynomial, not a Maclaurin, and it's evaluated at 3. Apologize for that mistake. There. Can you read all that? You understand what I'm doing here?
Yeah.
Okay. Well, they give us that number. F of 3 is 2. They give us f prime of 3, which is -1. And what must go with that is x minus 3. And then they give us f double prime of 3, which is 6. What must go with that is x minus 3 squared over 2 factorial. And finally, the fourth term, they tell us that the third derivative evaluated at 3 is 12. It has to be next to an x minus 3 to the third over 3 factorial. And again, with these answers, notice that we have to convert. That 6 divided by 2 factorial becomes a 3. Right?
Mm-hmm.
Okay, so if I convert that, take away the factorial, put the 3 there. And the next term is 12 divided by 3 factorial, which is 6. 12 divided by 6 is 2. Take away the factorial, put a 2 there, and look on there and see if we have that as an answer. And we do. 2 minus, because of that minus 1, x minus 3 plus 3 times x minus 3 plus 2 times x minus 3 cubed. So it looks maybe again like you didn't put the coefficient over the denominator.
Yeah, I did that a couple times.
Yeah, easy mistake to make with this stuff. Very easy. Kind of, you have to make it once or twice before you really figure out that you have to incorporate the denominator along with, in other words, the f double prime evaluated at either 0 or a is not the coefficient. That's just the numerator of the coefficient. Has to always be divided by that factorial. Well, let's see. I think that's everything you sent me, isn't it? I think we went over 4 pages of stuff. Hold on a minute. Let's see if there's anything else worth talking about here. The reason they want you to memorize these is so that you'll be able to do alterations of it. And here's a really good example of why infinite series are so important to calculus. If I want to do this problem, there is no antiderivative for that. I could search until I was blue in the face, and I will not find a function whose derivative is e to the minus x squared. So there's not really a good way to integrate this. But if we know that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, then what is e to the minus x squared equal to?
Just square all those, I suppose.
Well, again, you're substituting that wherever you see x. So it becomes 1 minus x squared minus, hold on. We'll use the original sign, plus, and in place of x, we're going to write minus x squared over 2 factorial. So you can see that I can figure out the infinite series for e to the minus x squared as long as I know what the power series for e to the x is. And now, instead of taking the integral of this, e to the minus x squared, I'm going to take the integral of 1 minus x squared plus x to the fourth over 2, and so forth and so on. And because I have the integral of the sum of a bunch of stuff, I can take the sum of the integrals. So I can integrate each of these terms separately. And even though I can't integrate the entire infinite series, if I integrated the first 4 terms of this, I would have a pretty good approximation for what e to the minus x squared was. So instead of integrating e to the minus x squared, I integrate each term of the infinite series that you get when you convert e to the minus x squared to an infinite series. And it basically gives me a way to integrate something that I had no way of integrating before. And this isn't the only function like that. There's lots of functions that do not have antiderivatives. And the way to integrate them is to convert them to an infinite series, which is much easier to integrate. Now, granted, you're only going to get an approximation. Since I can't actually integrate every term of this infinite series, usually the first 4 or 5 terms of an infinite series will give you a number that is within like 8 decimal places of accuracy to the original number. In other words, if I wanted to know, let's just make sure you understand what this means. If I wanted to know what the sine of 3 was, well, 3 radians. I could look it up on my calculator, but if I didn't have a calculator, I'd be plumb out of luck. I wouldn't have a clue as to how to come up with that. But if I use this approximation, what's it going to be equal to? If I use the first 4 terms of the expansion, which is all that is. So what's the sine of 3?
3 minus 27 over 3 factorial.
Okay, you got it. You understand how that can be used to approximate. Well, if I use just the first 4 terms of this, I'm going to get the sine of 3 to an accuracy of like 8 decimal places. That's how good infinite series are at approximating a number. And if you've ever wondered how they figured out what pi was, because I did lots of times, how have mathematicians figured out pi? They certainly didn't take a nice round circle and divide it by the diameter. Right? I mean, that's what pi is.
Yeah.
But you wouldn't be able to measure it accurately enough. So how did they come up with pi? Well, when they talk about having pi to 25,000 decimal places, they get it using these infinite series. I don't remember, it involves the arctangent, but if you use the arctangent function, one of the great mathematicians figured out that he could approximate pi to an accuracy of 9 decimal places by using merely the first 4 terms of an infinite series. And when you talk about pi being, there's people out there that claim to have memorized pi out to 25,000 decimal places. Well, how do you get each additional number on pi? You get it by taking one more term of the infinite series. In other words, maybe this is gotten by the first 2 terms of the infinite series, and to get the next digit, you got to take another term, and it just keeps giving you additional digits onto pi. And so if I took the first 100 terms of the infinite series that represents pi, maybe I'll get it out to 20,000 decimal places or something. But that's how pi is calculated accurately, is by using infinite series. And your book doesn't have the example on that, but my book actually does. My book actually gives me the infinite series as to how you go about getting pi. There's a couple of ways. You can use this arctangent series to figure out pi, but not as accurately. If you use like the first four terms, you don't get pi to a high degree of accuracy. Whereas the other method is the most accurate that any mathematician has come up with yet for determining pi to a high degree of accuracy. I can't even remember exactly what it is, but I know it involves the arctangent, the Arctangent Expansion. So are you done with chapter 9, or not really, probably, because we haven't really, well, we talked a little bit about radius of convergence and interval of convergence. But
yeah, a little bit.
This test here didn't really talk any of that. And you've not only got the interval of convergence, but you've got what happens at the end points. In other words, knowing the interval of convergence is not always everything. I might know the interval of convergence is -1 to 3, but now I got to figure out what goes on at -1. If it's convergent, then this becomes a bracket instead of a parentheses. And so once you come up with your interval of convergence, you go through and you check the two endpoints and see if that series is convergent when you use these endpoints. And if it is, you use a bracket instead of a parentheses. And you can have all combinations. You can have two parens, you can have two brackets, you can have left paren, right bracket, or left bracket, right paren. It just all depends on the particular function that you're looking at. But I haven't seen any questions regarding that, which leads me to believe you're not quite done with chapter 9.
No, we're on 9.3 right now.
Okay, good. So we'll be doing another session. If I could ask you one thing, and that is that when you go to chapter 10, when you make an appointment, if you could put a note in there that we've moved to chapter 10.
Okay.
Okay? And still try to send me the review material in advance. It's actually very helpful. I'm actually pretty impressed with your teacher, the way she does these. She gives you just enough information. She doesn't give you the answer, but she gives you enough information to kind of figure out how you should get the answer. She actually does give you the answer on these. But in our last session, she didn't. She just gave you a little bit of information as to how to really find the answer and how to show your work. And that's really helpful with calculus. There's calculus problems where a lot of times you just don't even know where to begin. But if you have the answer, you can almost work backwards. And it can be really, really helpful as figuring out where to begin. This one question that was e to the -6n, I actually went on Wolfram alpha. I couldn't figure that out at first because I was thinking about it wrong. And so I decided, I knew it was convergent, but I just had a hard time figuring out what it converged to. So I went on Wolfram alpha, and it gave me what it converged to, but it gave it to me simplified. So I had to go through what I had and do the algebra to come up with what Wolfram alpha had, and it was the same thing. It just looked like it. In other words, we had 1 over 1 minus 1 over e to the 6th. Well, that ends up being e to the 6th over e to the 6th minus 1. And that was the answer that Wolfram alpha had. And it's not that easy to turn that into that. I mean, it's a little sophisticated algebra, but that's all it is. So you do have to be a little bit careful, but seeing the answer on Wolfram alpha actually allowed me to work backwards and realize that it had to converge to that, which meant R was that, which meant that it was really, we were looking at e to the minus 6 to the n power. Let's talk about that just 1 second here, because this actually was an excellent illustration of something I was trying to point out before. So that turns into 1 over e to the 6th n, right? But I can also say that that's 1 over e all to the 6th n. In other words, whenever 1 is your numerator and you have your exponent in the denominator, you can make this conversion. Notice what I did there. Well, that's pretty valuable because that's going to be what R is. And the next thing I did was I took 1 over e to the 6th on the inside and took the whole thing to the n, or 1 to the minus 6th. Actually, what I did was this. I took 1 over e to the 6th and took that whole thing to the n. And now 1 over e to the 6th became my R of my geometric series. But this step here is not always that valuable. One other thing I was thinking about, as long as we have just a minute or two. Convergent or not?
Not. Or
correct.
Yeah, convergent.
No, it's divergent because it's a p-series. And p is equal to 1. In other words, there's a 1 right there. And as long as p is equal or greater or less than 1, it's a divergent series. But if I turn it into an alternating series that is exactly the same, except for having that, divergent or convergent. In other words, this series up here is basically 1 plus 1/2 plus 1/3. We knew all along that that was a divergent series. This series down here is 1 minus 1/2 plus 1/3 minus 1/4. That is a convergent series. In other words, merely by making it an alternating series, I turned it into a convergent series. And alternating series have their own special rule. Remember that one rule for something to be convergent is the nth term has to be 0 as n goes to infinity. Well, and that's what that means, is if I look at that, the nth term definitely goes to 0 as n goes to infinity. But that doesn't prove convergence. If you have an alternating series, there's one other thing you have to prove convergence. And that is that a sub n has to be greater than a sub n plus 1. Okay? In other words, if you have an alternating series, and the nth term goes to 0, and a sub n is greater than a sub n plus 1, then you have a convergent series. Well, what is a sub n? In this case, that's 1 over n. What is a sub n plus 1? That's 1 over n plus 1. And you can see that as long as n is positive, 1 over n is always going to be bigger than 1 over n plus 1. right? I'm increasing the denominator by 1, so it gets smaller. So this series is convergent because it satisfies that condition along with the nth term goes to 0. Up here, notice the nth term goes to 0 also, but that's a divergent series because it's not alternating. Making it alternating makes the difference. And the rules for an alternating series are different than the rules for a standard P series. The standard P series, just P has to be less than 1 for that thing to be convergent. But in the alternating series, notice that there is no P. It's the nth term of the series, and this is a sub n right here. It's not that. A sub n is the part exclusive of the minus 1 to the n.
Okay.
Okay, so that's really the difference between alternating, and that's the best illustration because it's the same series, only alternating. And one is convergent and one is divergent.
Yeah.
All right. I will let you go. And I would imagine we'll probably end up having one more session on Chapter 9.
I'd expect so.
And then we'll move to 10.
Sounds good.
All right.
All right. See ya.
Talk to you later. Bye-bye.